Introduction to the role played by Opera simulation software in the design of NDT devices. Opera has been in commercial development since 1984. In 2018, Opera joined Dassault Systèmes as part of the Simulia brand. Today we're looking at non-destructive testing, or NDT, which is the process used in the industry to evaluate the properties or integrity of a material without affecting its properties, so a device can continue to be used even after detailed inspection of its condition. In this presentation, we'll concentrate on two electromagnetic methods: magnetic flux leakage, as used for defect detection, and eddy current testing, which is sensitive enough to be used for gauging as well. Conventional eddy current testing is based on the fact that when a coil excited by an alternating current is brought in proximity to an electrically conducting material, eddy currents are induced, and the impedance measured at the terminals of the coil changes. The goal in the design process is to maximize sensitivity of the assembly. Finite element analysis, or FEA, is a numerical analysis technique. The domain is mesh using the finite elements of the process's name. The mesh will give discretization errors due to the approximations involved in the numerical solution process. These can be reduced by using more elements, mesh refinement as it's called, but they can never be completely eliminated. To eliminate errors introduced by mesh discretization, we can run two models, one with and one without the flaw present. The difference, therefore, is purely the effect of the flaw, not due to any FEA artifacts. In eddy current testing, the excitation of the problem will be by use of coils with, usually, an AC supply. In FEA, there are different ways of modeling coils. Which is most accurate and efficient can vary with the type of problem being solved. Firstly, we can use analytical representations of fixed current density coils. These are placed independent of the mesh. The conductors don't form part of the mesh in the solution. Hence, models can be easier to define, but post-processing may be more challenging, requiring derivations from flux leakage calculations rather than utilizing readily accessible circuit parameters. Alternately, we can use a filamentary representation or fully mesh the coil. Another practical consideration when performing FE analysis of eddy current NDT problems is skin depth modeling. It may be impractical, resource-wise, to mesh a whole problem with finite elements discretized to the size of the skin depth of the problem, so users need a way to accurately perform calculations at the surface, but utilize a coarser representation where the numerical integration points are unnecessary. In Opera 3D, a surface impedance boundary condition, or SIBC, can be applied to the external surface of a conducting volume. The SIBC treats all current as flowing on the surface of the material, and specific calculation techniques are used to employ to accurately capture the behavior of the fields. If the field in a specimen is very small, employing a volume mesh representation can cause unnecessarily complex geometry models. In this case, we can deploy the electric insulating boundary condition, or EIBC, in Opera 3D. Instead of modeling the gap or flaw explicitly as a small volume, it's represented as an infinitely thin break between materials by applying a surface boundary condition between the two conducting volumes. The International CompuMag Society have devised a series of open benchmarks known as T.E.A.M, specifically to test electromagnetic analysis software using problems with relevance for subjects such as NDT. For example, T.E.A.M problems 8 and 15 deal with benchmarks in modeling the accuracy of coils above cracks in metallic plates. Here we see the Opera model for T.E.A.M problem 8 for the case where the flaw is parallel to the motion of the coil. For electromagnetic problems, the air is modeled and you can see the mesh in grey. You can also see the plate and the area of the floor where the mesh has been refined to give a better approximation. A specific material assignment is used for the floor so that we can easily switch between steel and air without changing the mesh. Note also the representation of the drive coil. It's placed above the plate and is immersed in the mesh of the air, but the element edges do not have to coincide with the edges of the coil. Here we can see how the analysis database is prepared for T.E.A.M problem 8. We're running a script in Opera which places the coil at each of the positions defined in the T.E.A.M problem 8 specification. Because the analytical coil is independent of the mesh doesn't change as the coil is repositioned, which is a requirement if we want to eliminate mesh discretization errors for the most accurate results. We can create a number of solution cases in a single database, so we can generate one database for the plate with the flaw, then reassign materials and create a second database for the plate without a flaw. Here we see the results for the different coil positions specified in T.E.A.M problem 8, for the plate with no crack and the plate with a crack parallel to the direction of motion. We're displaying contours of flux density and vectors of current density. As mentioned previously, there's no motion accounted for in the analysis. We're merely solving multiple cases with a coil in different positions, so there are no eddy currents induced by motion effects in this case. We can see the flux linkage picked up by the two coils as real and imaginary components. The interesting thing to note is that the shape of the signal is different when the crack is perpendicular to the movement compared to when it's parallel to the movement. In an actual NDT device, there'd be 2 or even 3 probes measuring the return signal. Thus, from the relative shapes of the signal, not only can the presence of a flaw be detected, but also some information about its relative orientation. Flaws in different directions will have differing levels of severity, depending on how the structure is stressed. A full description of this problem is available on the website. Moving away from eddy current testing now and onto magnetic flux leakage, the MFL measurement principle is based on the fact that when strongly magnetizing a steel tube, some of the flux will leak out of the tube. Flaws in the tube that reduce the wall cross-section alter the leakage pattern. The shape of the flux leakage, therefore, is dependent upon the defect's geometry. The presence of the leakage field at the surface of the material can then be detected by sensors such as coils or Hall probes, or it can be observed visually using magnetic particle. The specimen to be tested is usually magnetized by applying a direct current, with the form of the coil dependent on the application, or using permanent magnets. Let's now take a look at some of the features of finite element analysis which are crucial in successful, efficient use for solving MFL simulations. Because the method relies on inducing a high magnetic flux density in the pipe, accurate nonlinear material modeling is a must. High-speed, non-destructive inspection systems using the MFL method are in great demand for online inspection and defect characterization, especially in pipeline maintenance. Such schemes aim to deduce the shape and dimensions of a flaw from the voltage induced in a pickup coil moving relatively quickly along the structure. MFL simulated with purely a velocity effect gives rise to an additional difficulty in both signal interpretation and modeling due to the formation of eddy currents when an excitation source moves over or inside a metallic pipeline. Numerical approaches to this problem include 2 schemes. Firstly, it can be solved quasi-statically with an extra movement component added to the formulation. Or secondly, the relative movement of the probe and pipe can be analysed over several time steps with the problem automatically repositioning and remeshing as the solution progresses. Static MFL methodology, or magnetic particle inspection, involves magnetizing a portion of the structure and recording the flux at the circuit surface. Usually, a local magnetization close to the saturation is required because the leakage flux amplitude is generally proportional to the magnetization level. For something like a bulk liquid storage tank, a magnetizing field of 1.5 to 2 Tesla is commonly used. This allows for scanning on both sides of the wall. Using a lower field might require multiple passes to fully determine the location of the flaw, and this can be difficult because of residual magnetism in the steel after passing over the MFL scanner. This type of device is commonly used on structures such as storage tanks, where the walls of flaw are subject to corrosion. When analysing a moving MFL system, you can make use of 2 different analysis types. Firstly, you can model a moving conductor in static field by merely applying a loading and assuming the cross-section of moving and conducting media are uniform. You might use this to check the saturation of the flux into the specimen. It will not predict the signal generated by a particular type or shape of flaw. For that, you'd need to use a transient analysis, whereby the pieces move relative to one another and the problem transiently remeshes as the solution progresses. Naturally, the former type of analysis takes less resources to perform. We'll now look at these 2 analysis types and what they might be used for. When running a problem whereby the mesh is constant and relative motion is applied as a velocity loading in a standard FEA solver, you'll risk non-convergence of the solution. The main reason is that diagonals of conventional FEA equations approach zero or even become negative when the velocity increases. The Opera 3D solver users in this instance, on the other hand, makes use of a technique called upwinding. This has allowed greater speeds to be defined without the need for overly refined meshes, and hence the solution times have been greatly improved over a standard solver. These two pictures show a coil moving at speed over a conducting plate. Without upwinding, you can see instabilities in the area ahead of the movement. When upwinding is enabled, the instability is completely removed. Now on to how magnetic flux leakage NDT testing is carried out in the field. A common piece of hardware used for MFL detection in the pipe is a pipeline inspection gauge, or PIG. A strong magnetic field is established in the pipe wall using either magnets or by injecting electrical current into the steel. Damaged areas of the pipe can't support as much magnetic flux as undamaged areas, so magnetic flux leaks out of the pipe wall at the damaged areas. An array of sensors around the circumference of the PIG detects the magnetic flux leakage and notes the area of damage. The purpose of performing simulation and design of a PIG is to optimize the shape and weight of the device against given performance criteria. The requirements that the tools saturate the pipe and provide maximum fluid bypass are inherently conflicting. Saturating the pipe requires a large area of steel inside the body of the tool to provide a return path for the magnetic flux. On the other hand, achieving maximum gas bypass requires a large bore in the center of the tool. Magnetic clamping forces are directly proportional to the flux magnitude in the gap. These clamping forces should be minimized so as not to adversely affect the smooth progress through the pipeline. With increasing speed, the magnetic field levels will decrease on the outer wall as the field is channeled away from the outside wall, so this must be factored into the design process. Long pole spacing will typically deliver lower magnetic flux densities in the pipe at low velocities, but these designs are more stable dynamically and provide better access for sensors, so there's a number of factors to consider in the basics of the design. For this design exercise, we use a dynamic solution whereby the relative motion is considered not to change the finite element geometry. The source fields and driving conductors are considered to be time invariant. We'll solve for only one position, so consider the PIG effectively to be moving along the inside of an infinitely long pipe. At the top of the animation is the pipe wall. We're starting at a very low speed, then increasing to beyond normal operating range, just to demonstrate what happens. At the higher velocities, the effect of the eddy currents and induced field become most evident. Since the applied fields will always be lower on the outer wall than the inner, the sensors must be calibrated for the difference. If the PIG is run too quickly, then the field levels on the outer wall may decrease to a level where reliable detection is no longer possible. In the previous example, we were looking at the design of a PIG in order to fully magnetize the pipe wall. We didn't look at the signal generated by a flaw. If we want to look at this in detail, we need to incorporate the flaw in the model and include its motion through the detection system. To demonstrate a simple setup for this type of NDT analysis, we use a moving cable with a rectangular defect. To induce the magnetic field, we're using two C-shaped formers with drive coils, and then a third coil acts as a pickup. Because the cable is moving relative to the drive coil and pickup, we'll solve the problem using a transient technique, whereby the cable with the defect is driven between the formers and we generate output at several points in time. In between each of these time steps, as they're called, Opera 3D will automatically remesh the problem to ensure that we retain a quality, undistorted, and hence accurate mesh. Once the problem's been solved, there are many ways to view the results within a post-processor. For example, the magnetic flux density can be viewed as contours or as vectors, as shown for a particular output time in the bottom left, and the output of the pickup coil can be seen responding to the flaw in the top right. In summary, Opera 3D includes simulation tools that are very effective for designing non-destructive testing equipment. Mesh-independent coils allow for easier definition of problems where the coil is moved to different positions, but you want to retain the same analysis mesh. For ease of modeling and accuracy, you'll need layering in solid meshes, or the option to use surface representations of both skin depth and or flaws. Relative motion needs special formulations to avoid convergence issues and deliver the accuracy you need with or without remeshing. Comprehensive post-processing functionality will be required to allow the necessary calculations for of defects. An optimizer can speed the development process of probes with conflicting goals and constraints. Thank you for joining us for this quick overview. Please do not hesitate to contact us for more information or check the website for further details.